Hey everyone, and welcome. Today, we're diving into something you've probably seen a million times, maybe in a clock or a science museum, the simple pendulum. Its swing seems so simple, right? But understanding it unlocks some really core principles of how things oscillate and move in a repeating pattern. So, let's break down the physics behind that predictable swing.
Here's our game plan. First, we'll get really clear on what we mean by an ideal simple pendulum. Then, we'll look at the actual forces that make it swing back and forth. After that, we'll jump into the math and figure out the formula that describes its timing. And finally, we'll take all that knowledge and use it to solve a few interesting problems.
All right, first things first, what is a simple pendulum? Well, in physics, we love to start with what we call an idealized model. It's basically a super simplified version of a real-world object. We strip away all the messy stuff like air resistance and friction so we can get right to the heart of the physics. So to build this perfect, ideal pendulum in our minds, we make a few key assumptions. The bob at the end, we pretend it's just a point with mass, no size. The string, we imagine it has zero weight and doesn't stretch at all. And the point it hangs from, totally frictionless. Now, of course, no pendulum in the real world is actually like this, but this perfect model lets us zero in on the essential physics of what makes it swing. Okay, so we know what it is, but why does it move the way it does? What are the forces at play that create that steady, repeating swing? Let's get into it. It all starts with gravity. No surprise there, right? The Earth is constantly pulling the bob straight down with a force we call its weight, which is just its mass times the gravitational acceleration, or mg. Now, if the pendulum is just hanging there, not moving, the tension in the string just cancels that force out. But the moment you pull it to the side, things get interesting. Here's the key idea. Gravity pulls straight down, but the bob swings along a curved path, an arc. So to really understand the motion, we have to break that weight force into two parts, or components. One component just pulls on the string, but the other one, this mg sine theta component, pulls the bob sideways, always trying to get it back to its lowest point. We call this the restoring force, and it's the real engine that drives the whole oscillation. Now, for this motion to be what physicists call true simple harmonic motion, or SHM, there's a really important condition. The angle of the swing, which we call theta, has to be small. We're talking less than about 10 degrees. Why? Because when the angle is that small, we can use a neat mathematical trick called the small angle approximation. It basically says that the sine of the angle is almost the same as the angle itself. And this little simplification leads to an absolutely mind-blowing consequence. The time it takes for a full swing doesn't depend on the mass of the bob or how far back you pull it. So, we've got the concepts down, we understand the forces and the conditions. Now let's translate all of this into the language of physics, mathematics. We're about to build the exact equation that tells us how to time a pendulum's swing. Let's walk through this step by step. First, we start with our restoring force. F equals negative mg sine theta. That negative sign is super important. It just means the force is always pulling the bob back toward the center. Step 2, we bring in Newton's legendary second law. F equals ma, so we set ma equal to our force. Step 3, here comes our trick, the small angle approximation. And finally, step 4, we substitute that in, and after a little cleanup, we get a beautifully simple expression for the bob's acceleration. We're almost there. Now, in step 5, we look at our result and realize it has the exact same structure as the general equation for simple harmonic motion. So by comparing our equation to the standard one, we can figure out the angular frequency, omega. You can think of omega as a measure of how fast the oscillation happens. It turns out omega squared is just g divided by L. And the final piece of the puzzle, step 7, is knowing that the period, t, is always 2 pi divided by that angular frequency. That leads us right to our final formula. And here it is, so beautiful. The time for one full swing, t, is equal to 2 pi times the square root of the pendulum's length, L, divided by the acceleration due to gravity, g. This formula perfectly captures the motion. And look closely, what's missing? Just like we predicted, there's no mass and there's no amplitude. For small swings, only two things matter: how long the string is and how strong gravity is. That's it. Okay, having the theory is one thing, but using it is how we really make it stick. So let's put this powerful formula to work and solve a couple of problems to see how it all plays out in practice. All right, here's a classic. A seconds pendulum is a special kind of pendulum.
Its period, the time for a full swing, is exactly 2 seconds. So 1 second to swing out and 1 second to swing back. The question is, how long does that pendulum need to be right here on Earth?
So to figure this out, we just take our formula and rearrange it to solve for L. We plug in 2.0 seconds for the period T and 9.8 meters per second squared for G. And what do we get? 0.992 meters. That's just under 1 meter long. It's this precise relationship that made pendulums so incredibly important for making accurate clocks for centuries.
Okay, let's switch things up. What if we took a 1.5 meter long pendulum to the moon? You know that gravity there is way weaker. So what do you think will happen to its swing? Is it going to be faster or is it going to be slower? So let's lay out what we know. The length, L, is 1.50 meters. The gravity on the moon, G, is a tiny 1.62 meters per second squared. We're looking for the new period, T. Let's just plug those numbers right into our formula. The answer is a full 6.0 seconds. Whoa! Back on Earth, this same pendulum would take about 2.5 seconds to swing back and forth. But on the moon, with its much weaker gravity, that restoring force is also much weaker. The whole oscillation happens in this beautiful slow motion. The period is way, way longer. Okay, pop quiz time, and you don't even need a calculator for this one. If you take a pendulum and you make the string 4 times longer, what happens to the time it takes to complete one full swing? Does it double, get cut in half, or become 4 times as long?
The correct answer is A, it's doubled. And the reason is right there in our formula. The period isn't proportional to the length, it's proportional to the square root of the length. So if you make the length 4 times bigger, the period increases by the square root of 4, which is 2. The period doubles.
And this all leads to a really cool final idea. We've seen just how precisely a pendulum's timing is tied to its length and the local gravity. So imagine this. An astronaut lands on an unexplored planet. All she has is a pendulum with a string of a known length and a simple stopwatch. What could she find out? Well, by timing the swing, she could work backwards using our formula to calculate the planet's gravitational acceleration. She could literally use a swinging rock on a string to weigh a whole new world. How amazing is that?